Welcome to the lecture 24. In this we are going to learn more examples on plastic design, plastic analysis and design. So, in the last lecture we learned two theorems, static and kinematic theorems, which are lower and upper bound theorems respectively, which are useful in computing the collapse load. We already learned that collapse load WC is obtained using either static theorem or kinematic theorem mostly, but we have also seen an example where both theorems are used. So, please do not mistake yourself in learning that these theorems are substitute each other. No, in fact they support each other. Okay. So, do not think that there is a substitution of this. I can only learn only one procedure, I can get rid of the other and I will still be able to get WC. That is the first thing we learned. Second thing, we also learned that WC is said to be obtained using iterative procedure, but we have not seen an example so far how this will be done from an iterative procedure. So, today we will see some examples where this will be learnt. We have also understood that collapse load is a function of MP and MP is known for a given section and material, because MP is actually stress Y, yield stress multiplied by Zp, where Zp is shape factor of Zy, and for standard sections given in steel handbook, especially with steel, Zy is a known value. Of course, we have also given you the MATLAB codes. We explain you the procedure for finding out the shape factor for different standard rolled steel sections. So, I believe that MP can be easily computed for a known material, for a known cross section, which is more or less identified as a geometric property. Okay. So, now the collapse load or the load at which this geometry is intended to collapse can be obtained by these two theorems, namely static and kinematic theorems. Okay. So, having said this, let us do few more examples to learn more in detail about the plastic analysis and also an example of the plastic design. So, we will in this lecture we say example 1, let us say we have a fixed beam subjected to a load as shown in the figure. Is an UDL of 20 kilonewton per meter. There is also a point load of 10 kilonewton and the geometric details are given like this. So, let us name this end as A and B and this point as C. Okay. Let us quickly ask a question before we solve this problem. Let us ask what is the degree of static indeterminacy of this problem. If we neglect axial deformation, then degree of indeterminacy is 4 minus 2, which is 2. So, how many plastic hinges do I need? The number of plastic hinges required to convert this beam into a mechanism is n plus 1, which will be 3. Now, the question comes where these hinges will form. Okay. For sure, these hinges shall form at support A and B. There is no doubt because they are fixed ends. But we have a doubt whether this will form at C being a concentrated load or anywhere on the span BC. Okay. So, let us try to examine this. So, we know that the beam is subjected to two set of loads. One is a concentrated load of 10 kilonewton, then an UDL of 20 kilonewton per meter for a span of 1 meter and 2 meters, 3 meters respectively. Let us use kinematic theorem. So, for kinematic theorem, I must draw the plastic deformation of this beam. Let us do that. So, we will assume a hinge here for sure, we will assume a hinge here for sure, and we will also have a hinge here for sure. You may wonder that for an uniform distributed load span, I am drawing a straight line. Friends, this is not the bending moment diagram, this is the deflected shape of the beam. Okay. So, this is the deflected shape of the beam. So, now let us mark these rotations. Let us call this theta 1. If we call this as theta 2, obviously this will be theta 1 plus theta 2 by simple mathematics, is it not? And let me call this vertical displacement as del. Okay. Then let us write down the external virtual work. There are two loads here. So, the point load multiplied by this displacement. When there is a UDL, we have to find the area. So, half into base into height into intensity of the load. So, which will give me 40 del. So, second one is internal virtual work. We have assumed plastic hinges at 3 locations as marked in green color. So, this is going to be MP of theta 1, which is at A, plus MP of theta 1 plus theta 2 at C, plus MP of theta 2 at B, because this is A, this is B, this point is C. So, which gives me it is 2 MP theta 1 plus theta 2. So, from the figure I can always relate theta and del. So, from the figure we can say for small displacements tan theta 1 is theta 1, which is del by 1, and tan theta 2 is theta 2, which is del by 3. Okay. Let me substitute these theta 1 and theta 2 as a function of del in this equation. Okay. So, by substituting and equating external virtual work to internal virtual work, there is principle of virtual work. I should say it is 40 del is 2 mp of theta 1 plus theta 2, which is 2 mp of del by 1 plus del by 3. So, now 40 del is 2 mp del of 1 plus 1 by 3. Okay, I can find mp now. It is a straightforward problem, right. So, this matches with the assumptions what we made in the number of plastic hinges formation, and I am able to get my mp. Okay. Where I consider this load will be the subjected load on the system. So, obtaining mp for the analysis is plastic design. So, now I am estimating the demand. Okay. The demand is 15 mp, sorry. The capacity of this beam is sigma y into Zp if we know the cross section. I can find this if I know the material strength. I can check. Demand should be always lesser than the capacity for safe design. Okay. Let us do one more example. Let us say we have a portal frame. We say estimate the collapse load of the portal frame. Let us draw the portal frame. Let us say the length or the span of the beam is L and height of the column is 2L, and the column has a capacity MP, whereas the beam also a capacity MP. I am marking MP because I know MP, because MP is actually sigma y into Zp. Zp depends on the cross section. So, I know Zp, I know the material strength, I know MP, therefore, I can mark these values. Let us say that the beam and column has the same strength. Now, this beam or this frame is subjected to two loads. One is a lateral load W, other is a vertical load which is 2W, which is eccentric. Okay, this distance of the load is L by 3, and of course, this distance is 2L by 3. Okay, let us name these joints or nodes, this as A, this as B, this as C, this as D. Okay, and we call this point as E. Let us try to find out the degree of static indeterminacy for this frame. Okay. So, there are two fixed supports. So, there will be 3 unknowns. So, the degree of indeterminacy will be 3 reactions at A plus 3 reactions at D minus number of equations of static equilibrium. We will say it is 6 minus 3, so 3. So, the number of plastic hinges required to form or to convert this portal frame into a mechanism will be n plus 1, which is 4. So, we need 4 plastic hinges. Let us ask a question, where these hinges will form? For sure they will form at A and D because they are fixed ends, and there is a possibility it can further form at B, C and E. So, there are 5 possible locations, I need only 4. So, plus recollect that there are different mechanisms available for analysis like beam mechanism, column mechanism or sway mechanism, combined mechanism, partial collapse mechanism, complete collapse mechanism, over collapse mechanism and so on. We learnt all of them in the previous lectures. Please turn back and learn and understand. Now friends, this problem is slightly tricky because we have got 5 possible locations, whereas I need only 4. Okay. So, we will use kinematic theorem to solve this problem. The kinematic theorem states I must assume a collapse mechanism first. Okay. Let us assume a beam mechanism. Which is going to be on the segment AEC or on the segment BC, okay, on the beam BC. Let us draw that beam separately. So, there is a load 2W here, this is L by 3, this is 2L by 3, okay. This is my deflected shape of the end B. So, let us assume that I have 3 hinges formed here. So, it is a partial collapse mechanism. So, I am assuming why a partial collapse mechanism? So, for a complete collapse mechanism I need 4 hinges, I have assumed only 3. Okay. Let me redraw this figure with this load 2W. I call this as A and this as B. So, let us say I will have hinges here. I can call this angle as theta 1, this angle as theta 2 and this displacement as del, and this angle will be theta 1 plus theta 2. Okay. Let us write down the external virtual work, which will be 2W into del. The internal virtual work will be the work done by the plastic hinges. So, I have one plastic hinge formed at B, I have one plastic hinge, this is B, this is C and this is E, one plastic hinge at C. So, this multiplied with, okay, let me MP into theta 1, this is at B, plus MP into theta 2, this is at C, plus MP into theta 1 plus theta 2, this is at E. So, which becomes 2 MP theta 1 plus theta 2. So, from the figure we also know theta 1 is del by A and theta 2 is del by B. So, let us equate external virtual work to internal virtual work, which is 2 W del should be equal to 2 MP times of del of 1 by A plus 1 by B, okay, which will be 2 MP del of A plus B by AB. Can I say A plus B as L from the figure? So, now 2 W del is 2 MP del L by AB. Therefore, I can say now the collapse load W is MP L by AB. But I cannot guarantee this is the final answer of the collapse load, because this has been obtained based on the partial collapse mechanism and looking only at the beam mechanism, right. There are other mechanisms possible. Let us extend this further. Let us say A is L by 3 and B is 2 L by 3. I can quickly get WC as 9 MP by 2 L. Okay, that is my answer. I call this as equation number 1. Okay. Equation 1 cannot confirm the collapse load for 2 reasons. 1, it is based on a partial collapse mechanism. 2, it is based only on a beam mechanism. There are other mechanisms possible. Let us look into the second option, which is a sway mechanism. Sway mechanism let us draw the deflected profile of the frame in the sway mode. Okay. So, I assume the plastic hinges are at A, B, C and D. That is, I think I can mark them here. Let me call this angle as alpha, which is also alpha. Let me call this displacement as delta. Let us write down the geometry. This is L and this is 2L, am I right? And this end is A, this is B, this is C and this is D. Okay. Let me now write down the, and there is a load applied, which is W here, is it not? And of course, there is a load applied here, which is 2W. Let us write down the external virtual work, which is going to be only W into delta, because this will not do any work as it has not undergone any displacement. And now, let us estimate the internal virtual work. So, one work done is here, it is rotated, other work done is here, it is rotated. The angle between the normals should be same, but there is only a strict sway here. The frame has just swayed. Therefore, I can now say the internal virtual work is mp into alpha at A plus mp into alpha at D. So, can I say this as 2 mp alpha? So, external virtual work equated to internal virtual work, W into delta should be 2 mp alpha, but alpha and delta are related. We can write down the relationship from the figure. We know alpha for small angles is delta by 2L. So, substituting this in the above equation, we get W into delta is 2 mp times of delta by 2L. So, therefore, WC is, there will be work done at sections B and C, which is again mp alpha plus mp alpha at C. So, let us say this is also added to this. So, let me put this as 4 mp. So, this becomes 4 mp delta by 2L. So, it is 2 mp by L. So, friends, one value gives me collapse load as 9 mp by 2L, which is about 4.5 mp by L. The other one gives me it is 2 mp by L. So, now second equation, the collapse load given by second equation is again only based on sway mechanism, but it is a complete mechanism because there are 4 hinges. But still there is a question whether the hinge will form at E or B or C. See, the possible locations are A, D, B, C, E. We have 5 locations, but we need only 4, out of which A and D are sure because they are supports, they are fixed supports. But out of B, C and E, we have assumed that B and E, but we left out C because there is a question. So, this is also may not be the correct answer. Okay. Let us do one more attempt, one more iteration to find out using a combined mechanism. Let us draw the frame . And let us draw the combined mechanism including the sway and the beam. Let us assume the hinges, of course, at A and D for sure. Let us assume the hinge here and here. We will not assume hinge here. So, we are assuming hinges at A, D, C and E. So, there is a point load of 2W here, there is a lateral load of W here. Okay. So, we call this value as alpha, which is also alpha here. is also alpha, is also alpha, is also alpha, and we call this as delta, and we call this as del. Okay? And we call this angle as theta 1 and this angle as theta 2. Let us not put as alpha. Okay? Let us write down the external virtual work. The external virtual work will be 2W into delta, that is by the vertical load, 2W into del plus W into delta, that is the horizontal load. Let us write down the internal virtual work. We have 4 hinges. Okay. So, we should say MP into alpha, which is at A, okay, plus MP, see this is theta 1 plus theta 2, theta 1 plus theta 2 which is going to occur at E, plus MP into alpha plus theta 2 plus this is at C plus MP into alpha at D. So, which can be said as MP times of 3 alpha plus theta 1 plus 2 theta 2. Okay, 3 alpha, 1 here and 1 here, theta 1 is here, theta 2 is here and here. Okay, the internal virtual work. Now, I can find the relationship between delta and alpha. So, alpha is delta, this is 2L, let us mark that here, and this is L. So, alpha is delta by 2L, okay. So, I can replace alpha in terms of delta. Let us also find out relationship between theta and del and theta 2, that is theta 1 is del by L by 2, which is 2 del by L, and theta 2 is also del by L by 2, which is 2 del by L. Okay. So, we will substitute this. So, we have theta 1, we have theta 2 and we have alpha and del. So, we have equations in terms of del and delta. Okay. So, we now will replace this in del and delta. So, let us do that. We know alpha is delta by 2L, am I right? Yeah, delta by 2L. So, I should say delta is 2 alpha L, okay. And we have theta 1 as 2 del by L and theta 2 also as 2 del by L. So, let us write down the external virtual work, which is equal to 2 W del plus W delta internal virtual work, which was this one, MP times of 3 alpha plus theta 1 plus 2 theta 2, MP times of 3 alpha plus theta 1 plus 2 theta 2. Let us substitute them back. We will equate external virtual work to internal virtual work. So, 2 W del plus W delta should be MP times of 3 alpha plus theta 1 plus 2 theta 2. Okay. So, let us express everything. So, let us say W times of 2 del plus 2 alpha L, which will be equal to MP times of 3 alpha plus theta 1 plus 2 theta 2. So, in this figure, if you look at friends, I can say alpha and theta 2 and alpha and theta 1, because the angle between the normal has got to be same. So, using that condition, I can say alpha should be equivalent to theta 1 to theta 2, because angle between the normals is same. That is, in the displaced position, we consider this angle as still 90 degrees. Okay, we consider this angle still as 90 degrees between the members is 90 degrees. Okay. We simplify this and try to find WC. We will give you the answer in the next lecture. What would be this value? Please work out this and check up and tell me what is the WC from the combined mechanism, and therefore, what is the true collapse load of this beam. Okay. Thank you very much. Have a good day. Bye.